In this module, we are going to discuss the convolution property of continuous time Fourier transform. And this property is of major importance in signals and systems analysis. In fact, we will see the application and utility of this property in the context of frequency selective filtering. Sometimes we also use this property to bypass a convolution operation in time domain because with the help of this property, we can perform convolution entirely in the frequency domain by working with the Fourier transform and the inverse Fourier transform of the signals. Now, since convolution mostly arises in the discussions of LTI systems, here we have an LTI system whose impulse response is ht. The output of the system yt to an input signal xt is xt convolution ht, where the star represents a convolution operation. And if we expand this operation, we get this convolution integral. Now, the convolution property says that if yt is the convolution of two signals xt and ht, then its Fourier transform yj omega is equal to xj omega times hj omega. That is, the Fourier transform of convolution of two signals is the product of their Fourier transforms. And we will do a proof of this property as well. So to prove this property, we start from yj omega, which is the Fourier transform of yt, and then in place of yt, we replace the convolution integral minus infinity to infinity. So yt is a convolution of xt and ht, x tau, ht minus tau, d tau, e minus j omega t times dt. And now we bring this integral inside and change the order of few terms. Ht minus tau e minus j omega t dt times d tau. Here, this thing, we can immediately recognize that it is the Fourier transform of ht minus tau. And with the help of time shifting property, we know that the Fourier transform of ht minus tau is e minus j omega tau times h j omega d tau. Now we can pull h j omega out of this integral and we are left with x tau times e minus j omega tau times d tau. And this whole thing is the Fourier transform of xt. And here we have the proof of this property. Fourier transform of convolution of xt and ht is equal to the product of the Fourier transform of xt and the Fourier transform of ht. Now, in the context of LTI systems, we discuss few interesting things. Hj omega is the Fourier transform of ht, where ht is the impulse response of LTI systems. And we call Hj omega the frequency response of the system. So Hj omega is the frequency response of LTI systems. Why this name is appropriate? Because Hj omega, by looking at here, it captures the changes in the complex amplitude of the Fourier transform of the input signal. And like H HT, since HT completely characterizes an LTI system, so does the Hj omega. So let me write it over here like HT, Hj omega also completely characterizes an LTI system. And moreover, many of the properties of LTI systems that we have seen before can be conveniently interpreted in terms of the frequency response and this convolution property. For example, if we recall, if we have a cascade of two LTI systems, H1T and H2T, H1 and H2 are both LTI systems, and here we have a cascade of these two systems. We know that the overall impulse response of this system, if we call it HT, it is the convolution of H1T and H2T. And now with the help of this convolution property, we know that the overall frequency response of this system, Hj omega, is the product of H1 j omega and H2 j omega. So we can equivalently represent this cascaded system in this way, Yt. And since multiplication is commutative, so therefore we can immediately know that the order in which we put these systems, the order of the cascade, it actually does not matter. In fact, we can first pass xt through H2 j omega and followed by H1 j omega, and we will get the same response Yt. Okay, a few more things. Now if we once again write down this property, Yj omega is the product of Xj omega times H j omega. If we work out the magnitudes and phases, so magnitude Y j omega E phase of Y j omega is equal to magnitude of X j omega phase of X j omega and magnitude of H j omega angle H j omega. And now we can clearly see from here that the magnitude of the output signal is the product of these two magnitudes. So magnitudes multiply and the phase of Yj omega is equal to the phase of Xj omega plus the phase of Hj omega, and the phases add. Now the spectrum Yj omega at the output of an LTI system, because Yj omega is the product of Xj omega and Hj omega. The output spectrum cannot be any bigger than Xj omega or Hj omega because of the multiplication operation. So at the output of LTI system, the spectrum Yj omega cannot be any bigger than Xj omega or Hj omega. In fact, we can also say that an LTI system does not add any new frequencies at the output. So we can also put it down in LTI systems. No new frequencies can be added to the output spectrum Yj omega. And all these things, they are actually very evident from this convolution property, because Yj omega is the product of Xj omega and Hj omega, and these are all the consequences of this property. In fact, in filter design, what we do, we modify the spectral content of the input signal xt by designing a system whose frequency response is Hj omega, and basically what we do, most of the times we zero some portions of the input spectrum with the help of Hj omega. And these operations, filter design operations, they can be more easily visualized in the frequency domain with the help of this property. Now let us see an example. In this example, we will see the application of the convolution property, and we will also learn frequency selective filtering. Suppose from some circuit or some application, we got a signal xt whose spectrum looks like this. And in the spectrum, we see a lot of frequencies. However, we do not need all the frequencies in the signal, and we want to suppress the frequencies which are greater than omega c and which are less than minus omega c. That is, we only need frequencies in this range from minus WC to WC, and we want to suppress all the frequencies outside this range. Now, based on the convolution property, if we can design a system Hj omega, and the frequency response Hj omega after multiplication with the given Xj omega should produce a response Yj omega, that should be Xj omega if omega is less than omega c and 0 for omega greater than omega c. So this objective can be achieved if Hj omega is 1 and 0 for this range of frequencies. That is, all we need is a system with a frequency response that looks like this. So this is the pass band, and this system should stop all these frequencies that are outside this range. And this system is typically called ideal low pass filter. So if we design an ideal low pass filter, then at the output we will see a frequency, we will see an output yt, which will only contain the frequencies of xj omega in our desired range. So the output response will look like this. We will see this, something like this, minus omega c. This will be our yg omega. So here multiplication property, here the convolution property has helped us in solving this problem. And the impulse response ht of this filter is the Fourier inverse of h j omega, and we know that it is sinc sine omega ct divided by pi t. The impulse response, it looks something like this. Ht is the impulse response of an ideal low-pass filter. Now, I would also like to highlight few things here. Ideal low-pass filter is difficult to implement in practice. Why? Because its impulse response is non-causal and it has ripples. So frequency domain characteristics of this filter are ideal, but the time domain characteristics are generally not acceptable. So typically what we do, we perform a trade-off, that is we lose some ideality in the frequency domain in order to achieve better time domain features. And due to these reasons, the design of practical filters is generally a challenging thing.